Throughout organic chemistry, reactions that form carbon bonds tend to be relatively uncommon, right? In most cases, our more electronegative atoms, which then of course tend to be good nucleophiles, tend to be our key reactive elements that are then attacking other atoms in order to form new bonds. However, we have seen a few cases where we can make nucleophilic carbons that will then react with other carbons in order to form new carbon-carbon bonds. One great example of this is our reactions with Grignard reagents, right? So we had our organometallic compound where that carbon to magnesium bond was highly polarized towards our carbon. So then we had our nucleophilic carbon attack our electrophilic carbon and our carbonyl in order to create an alcohol. In today's lecture, we're going to be looking at some more examples of how we can use carbonyls, which of course have an electrophilic carbon, as our oxygen is pulling electron density away from our carbon here. Again, remember, we can always indicate that movement of electrons with our dipole arrow, creating our nucleophilic oxygen in our carbonyl compounds and our electrophilic carbon. As we've previously seen, we can see a variety of nucleophilic addition reactions based on this dipole, with nucleophiles adding onto our carbon, and of course then our oxygen taking those extra electrons. So we're going to see how we can use some additional carbon-based nucleophiles in order to create new carbon-carbon bonds with carbonyls. The first example that we'll look at today is cyanohydrin formation using our nucleophilic cyanide ion. So last semester we looked at cyanide, which is a good nucleophile because we have a carbanion bonded to our nitrogen. So we've seen this used in substitution reactions before. We can use that cyanide to substitute with our good halogen leaving groups in order to create these cyanide-based compounds. So our cyanohydrin is just what happens when we take our carbonyl and add on that cyanide here, and then of course we have our hydroxy group combined with that nitrile of our cyanide added on there as well. So in this reaction, we're going to be taking our carbonyl, again of course acting as our electrophile here with our electrophilic carbon, and we're bringing in our cyanide ion as our nucleophile. Now we could also use our hydrogen cyanide, HCN, which would then be giving us an acidic solution here. But the key nucleophile is usually going to be that cyanide ion itself. So in most cases we'll just add our cyanide ion and then add acid as a separate step in order to form our cyanohydrin product. Now the actual reaction here is going to be very familiar to what we've seen before with our Grignard reagents. So of course that good nucleophile is going to attack our electrophile here, and our electrons of this double bond then move out of the way up to the oxygen, which of course wants those extra electrons since it's more electronegative. And this results in our addition product with our electrons moved up to our oxygen and our new carbon and nitrogen forming our nitrile functional group added onto our carbonyl. Now, of course, that second step with our acid, we simply protonate our nucleophilic and basic oxygen here, and that leads us to our cyanohydrin. So again, you should notice the similarities here between our Grignard reagents attacking our carbonyls versus our cyanide ion here attacking. In this case, we just have created that nucleophilic carbon through our cyanide ion instead of through our organometallic compound. Now, of course, this sort of cyanohydrin formation reaction is going to be affected by the structure of our carbonyl in the same way that we saw with our hydration or our acetyl or ketyl formation reactions. Right? So that means that aldehydes, of course, are more likely to react, they're more likely to favor our product, whereas as we add in more crowding with our ketones or extra groups attached near our ketone, that will actually drive this reaction back towards our ketone, and we're unlikely to get much of our cyanohydrin forming. Right? So we do want to consider the structure of our carbonyl reactant in the same way as we've looked at previously. The next reaction that we're going to look at is the Wittig reaction. This reaction is a unique reaction that uses phosphorus to react with our carbonyl to create an alkene. So in some ways you can look at this as the reverse of our ozonolysis reaction, because we're actually going to be combining that carbonyl with another double bond in order to create an alkene. So essentially what we're doing here is taking our carbon chain from our carbonyl, right? So these two carbons, whatever that looks like, and we're combining that with the carbon chain from our compound over here, which we call a ylide, and we're adding those together to make our final alkene. Right, so each of these two portions are coming from our individual groups that we had in our reactants. Now let's take a closer look at the mechanism of this reaction. So in order to create this unique reaction, we need this key reagent here of our ylide. So our ylide is going to be formed from a triphenylphosphine, which that's what's shown here. Our pH3 is referring to 3 phenyl groups, or 3 benzene rings, attached to our phosphorus there. So initially, this would be our triphenylphosphine. Our phosphorus, of course, has 5 valence electrons, which means it has 3 bonds and 1 lone pair. Now, if we combine this with a alkyl halide, such as our, so I'm going to go with a 2-bromobutane here. So we've got our alkyl halide here, of course, which, as we know, will undergo substitution reactions. Our phosphorus here with that extra lone pair can actually act as a nucleophile. We can attack this, kick off our bromine leaving group, and that gives us our compound here. Again, I'm abbreviating these 3 large benzene rings as phenyl substituents coming off of my phosphorus. And now I have my new bond to my carbon chain. So I show my 4 carbons here from my 2-bromobutane. My phosphorus, of course, will have a positive charge since it lost 1 lone pair as it formed that new bond to my carbon here. Now, of course, at this carbon here, so I have my 2 bonds to other carbons. I also have a bond to a hydrogen, and of course the new bond that formed to my phosphorus. If I now add a strong base, of course the base will deprotonate this, and we can form a double bond there to form that ylide reagent. So now I have my ylide here with my carbon double bond to my phosphorus, my 3 benzene rings attached there, and of course whatever carbon chain I want based on the structure of my alkyl halide. Now the unique thing about my ylide here, right, is phosphorus is, it's in the same group as nitrogen, but it's of course lower down on the periodic table. So that means that it's actually not all that electronegative, and so my carbon here will actually tend to take the electrons in this double bond. So sometimes you'll see it drawn like this, with the double bond between my phosphorus and my carbon, but similar to my organometallic compounds, it's actually accurate to represent that as my carbon with my lone pair and my negative charge, and my phosphorus with a positive charge there as it donates those extra electrons to my carbon. So once again, using this unique ylide, what we've done is we've created a new nucleophile with our nucleophilic carbon here. So now for our actual Wittig reaction here, we're going to combine that with the electrophile in our carbonyl in order to create this new addition product with our carbon-carbon bonds forming here. So now that we have our ylide with our nucleophilic carbon, we can of course attack our electrophilic carbon of our carbonyl as normal. Now as we make that attack, of course our electrons need to move out of the way to make room for that new bond. And that's going to result with our negatively charged oxygen over here, that's highly nucleophilic, as we're adding on our new bond here. Now, since our oxygen is negative and highly nucleophilic, but we also have a phosphorus over here that's positively charged, we're actually going to attack from our oxygen over to our phosphorus at the same time. So essentially, the double bond of our carbonyl and the double bond of our ylide are attacking each other simultaneously in kind of a cyclic movement of electrons. And we're actually going to produce an intermediate here where we have a four-membered cyclic system. So we have our phosphorus bonded to our oxygen, which bonded, of course, to its carbon chain here. We've got our four carbons there of our butanol. Our phosphorus has its bond to our carbon here, which of course is our carbon of our butane. These are bonded together as our nucleophilic carbon of our ylide attack the electrophilic carbon of our carbonyl. And of course, our phosphorus here still has our three phenyl groups attached. So we actually currently have 5 bonds to our oxygen, or to our phosphorus, and of course our 2 bonds to our oxygen and our 4 bonds for each of our carbons. Remember that this carbon would have 1 additional hydrogen bonded on here as well. Phosphorus, of course, is okay with those 5 bonds because it's lower down the periodic table, which means that it has those d orbitals available as well. Now, once we have our intermediate here, this is going to break up in order to form our final alkene product. So our carbon can take those extra electrons away from our phosphorus in order to form a double bond down here, and our oxygen is going to take those extra electrons and form a double bond up here between our phosphorus and our oxygen. Now this reaction is highly favored because our phosphorus-oxygen bonds are actually quite strong and stable. So that kind of acts as the driving force for this reaction. So of course, once we have that movement of our electrons here, we end up with our triphenylphosphine bonded now to our oxygen, right? That's our side product up here. But of course, the main product that we care about is our alkene down here. So I'm going to go ahead and draw this in different colors. So I'm going to draw the blue of our compound from our ylide, our alkyl chain that is. So we're going to have our carbons up here. And then I'm going to draw here in green, we have our double bonds to our carbon chain that we got from our carbonyl. Notice that our new alkene here forms in the trans diastereomer specifically. This is preferred just based on the correct arrangement of our atoms here within our intermediate. So we get these groups over here from our carbonyl. And of course, these groups over here are coming from that ylide. And they're combining together to make our alkene. Essentially what we can look at it is we are eliminating the oxygen and the phosphorus and just plugging our 2 carbon chains together. Right? So we had our 4 carbons on one side from our ylide, and then the bond to our phosphorus is where we add on the additional 4 carbons from our carbonyl. So again, I can just look at it as attaching these 4 carbons on right where I had my phosphorus. So I'll just draw that out again in a different way from my drawing over there. Right? So there's my carbon chain from my ylide. And I'll use orange this time to attach my 4 carbons from my carbonyl to make my new alkene. Notice again, this is trans with my 2 longer chains on pointing in opposite directions for my double bond. And of course my shorter chain is cis relative to my long chain over here. But the overall conformation is trans. Again, the end result of my Wittig reaction is the production of a new alkene from my smaller carbonyl combined with my ylide. I can of course change what my alkene looks like based on what carbon chains I have here, whether it's an aldehyde or a ketone. And of course my ylide itself is going to be controlled by what alkyl halide I use. So I can vary that up as well depending on what I want my carbon chains to look like here in my alkene. Now in all the different reactions that we've looked at today, so we've seen different ways to create nucleophilic carbons, whether it's our ylide or our cyanide, and then attack our electrophilic carbon of our carbonyl in order to create new carbon-carbon bonds. So we see here that our carbonyls are quite useful for creating carbon-carbon bonds, again because they create that highly electrophilic carbon here due to the electronegativity of our oxygen, creating that large dipole between our carbon and our oxygen of our carbonyl compounds.